2.2, graphing rational functions. So rationals, you remember from grade 11 are, well, there's examples right here, where you have a polynomial on top, polynomial on the bottom. The only difference is the bottom or the denominator polynomial cannot be equal to 0, right? Because then we get undefined. So these are some rational functions here, right? 3 over x, 3x plus 20 over x plus, or x minus 3, and 4 over x minus 3 plus 2. So there's lots of different versions. So what we're going to do is let's look at the basic one. Let's look at y equals 1 over x. So the original would be y equals x, right? So y equals x is just the black line on here, right? You can see that. And when we take the when we do the rational of it, it's 1 over that. So there's some really key points here. And again, the invariant points is coming back. So 1, 1 on both graphs, right? If you plug in x is 1 here and y equals 1, right? And if you do that over here, x is 1, y equals 1. So, and it works for negative. So that point there, that red dot and that red dot, these ones right here are invariant points. That's the key thing here. So what the rest of it is we did a bit of graphing in grade 11 on this one. If you're struggling with this, you can look at, do a table of values. But as this approaches it, right, see, it gets closer and closer to the x-axis, and this one gets closer and closer to the y-axis. And then this point here. Now, why is there no point in the center? That's the question there. Well, that would be 0, 0. So if x was 0, it'd be 1 over 0. And we know already that you can't have a denominator of 0 because it's undefined. So there's nothing there. So again, if you were to graph the original one, this would be a dotted line, this black one, right? And then you would draw your red one in here, whatever color you pick, as your new 1 over x. So that's a really kind of key thing, is this main graph, because that helps us when we're graphing other things. Okay, so flip page and let's look at some other stuff here. So next one, several things should become clear, right? The point of discontinuity, there could be a hole in the graph. So what it happens is if a factor appears both in both the numerator and the denominator. Now, what we're going to do is we're going to do a whole bunch of rules. Don't stress too much. In the next lesson, 2.3, the rules are laid out really, really clearly. This is just to give you kind of an idea of what we're doing. So if a factor appears only in the denominator, we get a vertical asymptote. We've done that from in grade 11, right? We get the old vertical asymptotes, right? We know that. No, any x value that results in the denominator 0 is called a non-permissible value. So what we're going to see is we're also going to see now, in grade 11, our horizontal asymptote was always on the x-axis. In grade 12, it's going to start moving up or down. And we can also get something called an oblique asymptote. Now, an oblique is just another fancy word for a line going like, left and going up to the right, or going from the top left down to the bottom right, right? It's just an oblique asymptote. So if the degree of the numerator is equal to or smaller than the degree of the numerator, right? If they're exactly the same, you get a horizontal asymptote. If the degree of the numerator is greater than the degree of the denominator, you get an oblique asymptote. And again, like I said, don't stress too much about this right now. The rules are going to be really clear in 2.3. This is just kind of a pre-lesson to that whole thing. So these are just different things that you're going to look. And this is all rationals, right? Vertical, horizontal, oblique. And there's going to be one more, which is kind of weird. Oh, no, that's coming up. Sorry. Here, let's look at this one here, next page. If the degree of the numerator and the degree of the denominator, right, for instance, if they're the same, see how they're both x squares and x squares? Well, what you do is you look at the leading coefficient. So here we got a 3, and here we got a 1. You divide them, well, that creates your new horizontal asymptote. And again, look at this one. This is 3x squared plus 2x minus 3 over x squared minus 2x. Look at all the lines on here. You're probably not going to get one this complex, and if you do, I'll give you a question, and I'll give you a picture of it, and then ask you different questions about it. But that's just to show you that that's a horizontal asymptote. Now, let's look at the oblique one, which is on the next page there. These are kind of weird. You barely ever see them, but you still have to learn about them. Okay, so this one, if the degree of the numerator is larger than the degree of the denominator. So this one we have an x squared, this one we have an x to the 1. So you can see right away that the numerator is larger degree than the denominator. So what we do is we use division to change the form, right? And then we rewrite it. So what we do is we do good old synthetic division, right? So synthetic division, we have x squared, so we need a 1, a 0, and a 0. Excuse me. And then we put our negative 1 out here, because whatever we plug into here to make that 0. And then we do synthetic division, and we get 1, which is our x minus 1, and then our 1 plus x plus 1. That's the way to write it out. So what this is what this tells us is x minus 1, you could graph that. It's y equals x minus 1, and it's an oblique asymptote. So, right, when we look at it, see that line here, the main line here, the green line? That's our x minus 1. That is going to be our asymptote. And normally you don't put that in there. We just wrote it in here because it shows the graph. And then you get, look at the weird shape of this one. Wow. Again, you probably use a table of values. Now, this one, the oblique asymptote, you'll barely ever see it, but we still need to cover. And again, all of this will become a little clearer in 2.3 as you roll through this. Okay, so next page. So here we go. So graph y equals 4x minus 5 over x minus 2, and identify any asymptotes and intercepts. So here's some cool things. So we have, excuse me, we have x minus 2. So we know there will be a vertical asymptote at x equals positive 2 because our NPV, right, our non-permissible value, is at x equals 2. Because if we plug 2 into this thing in the bottom, in the denominator, it's going to equal 0. So there is our vertical asymptote. That's from grade 11. That hasn't changed. That's the standard way to do stuff. Now, what's changed, though, is, look, the degree of the top is a 1, and the degree of the bottom, the denominator, is also 1. So to find the horizontal asymptote, what we need to do is we need to take the leading coefficients, which is 4 divided by 1, which is 4. So we now have a horizontal asymptote at 4. Oh, okay. And we do dotted lines here, right? And we label them, you know, y equals 4, and then the vertical was x equals 2. So now how do we get the general shape? Well, this is the standard way. It's going to be up. It's going to be like if the red lines were quadrants, it's going to be like 1 and 3. And then the other version would be if there was maybe a negative there, it might be 2 and 4. Then there's going to be some weird cases where it's 1 and 2, right? You'll see these coming up. There's some interesting ones coming up. So then how do we find the rest of the values? Well, just make a table of values, right? Pick some x's, plug them in. When we plug these ones in, we get some weird points like 5.5 and 4.5. But it's just to give you the general shape, right? One of the useful ones would be to find the y-intercept, and that's easy, right? You just set x equal to 0, and you set up your y-intercept, so that's 5 over 2. So, right, 2.5. So if we look back at our graph, yeah, 2.5, there it is there. To find the x-intercept, if there was one, set y equal to 0, work backwards, and you can find out it's 5 over 4 or 1.25, right? So those are some key points. Even if you find, here's the thing, if you find the y-intercept and the x-intercept, that should give you the general shape. Now remember, you're sketching these things, right? So, I mean, label your key points. So your key points, you would label all your asymptotes and your dots. Those are the kind of the key points. Okay, flip the page. Let's look at another one here. So by transforming the graph of y equals 1 over x, create the graph of y equals 6 over 2 minus x minus 3. So where is our original graph? So where's our y equals 1 over x? Well, we can see that right away. That would be the black lines here. And again, there's your invariant points, right? The 1, 1 and the negative 1, 1. So what happens? Well, we have a new vertical asymptote at 2, right? Because it's what the denominator here, right? It's a 2, so it'd be 2 to the right. New horizontal asymptote is down 3. And what that does is because it's written this way, the negative 3 drops it down 3. So we have new and we have new. So then what you do is you just look at all your points and move them, right? 1, 1, that point is going to become 3, 3. If you wanted to find more, you could plug in x equals 3, right? So there, here it is. 1, negative 9 becomes 1, negative 9, right? And you can do more checkpoints. You can find like 4 and 0 and 0 and negative 6, the x and y intercepts. And again, so here's the new one, is the red one here with key points. And again, if you're struggling with this, if you don't understand how graphs move, table of values always work. So we can deal with this here, plug in our new table of values and create some points and graph it based on that. Okay. One more example, I think, last page. Rewrite the equation. Now look at this one here. So there's lots of ways to look at this. We got 3x minus 2, x minus 1. So we can look at it into a form that's easily graphed. So we can do synthetic division if we want, right? So we have a 3 and a negative 2. We plug in a negative 1 in the front because that's what would make this 0. Drop your number, multiply, you know the rule. So we end up with 3 and negative 5 over x plus 1. Okay. So what we can do is we can see a couple things. It would take the original graph, right, and this plus 3, even though it's out the front there, right, would shift it up. Now, if you look at this one, if you notice the degree here is the same degree here, so you could look at the leading coefficients. 3 divided by 1 is 3. So there's multiple ways of looking at this to try to change your horizontal asymptote. Where do we get the vertical asymptote from? Well, what do we plug into there, this right here, to make that equal to 0? Well, negative 1. There's your vertical asymptote. And again, general shape, then you can do that with a table of values. So like I said, this is kind of an introduction to the rules of graphing for rationals. Once you look at 2.3, right, it'll make a lot more sense because we broke the lesson down into very, very distinct parts. So we're only going to add one more thing, and that's called a point of discontinuity, or there's basically a hole in the graph, and you'll see that right away coming up in 2.3. Okay,